Hi everyone, my name is Olio,
And I'm Solari Azadi.
and for our CpE Technology Lab final project, we decided to create the snake game.
Introduction. Snake Game was first published by Nokia for monochrome phones. It was programmed in 1997 by Tenno Armanto of Nokia and introduced by the Nokia 66110. How does the game work? The game continues until the snake dies. A snake dies by either running into its edge of the board or by running its own tail. The final score is based on the number of apples eaten by the snake. The highest score recorded has been 252 points, which is 252 apples. Project overview. The standard rules of the game. An apple is generated randomly on the map. Snake starts out small and it eats more apples and it will gradually get longer. Snake dies once it collides with itself or a wall that is in the most outer parameter. This system is coded in a system Verilog, simulated in Quadris 2, implemented using a DO2 115 board, displayed into a monitor using a VGA cable, a PS2 keyboard connected into a D2 115 board for the control.
And now we're going to talk about the specifics of the system Verilog code for the project. So for this project, our code was composed of one top-level module and 4 lower-level modules. We also have a wrapper that instantiates the top-level module for the D2-115 board. Our top-level module is named Top-Level Snake. Our 4 lower-level modules are named VGA Slow Clock, Snake VGA, Snake Grid, and Keyboard. And as you can see on the image on the right, this is what our module for our wrapper looks like. And as I mentioned earlier, it instantiates our top level module, which is this thing right here. Now, I'm going to talk about the specifics of each module. First, we have the VGA Slow Clock module, which divides the 50 MHz clock by 2 so that we can get a 25 MHz clock for the VGA display. The Snake VGA module generates the display area and the borders around the edges of the screen, which, if the snake hits, will die and will cause the game to reset. The Snake Grid module randomly chooses a location on the display for the apple to appear in. The Keyboard module is for the PS2 keyboard to be able to control the snake with the given input keys. And as you can see in the image on the right, this is what our module for the VGA Slow Clock looks like, which divides the 50 MHz input by 2. And as you can see, it does this at every rising edge. If the signal is a reset, then the clock VGA will be set to 0. Otherwise, the clock VGA will be set to not clock VGA.
Block diagram. This portion of the overall block diagram shows the schematic of the keyboard model. As you can see, this register takes 2 inputs, clock, keyboard, and data. And the result are the 2 outputs. The first one is a 5-bit 1-odd output called direction that denotes which direction the snake will travel in. The second output is called reset, for we want to reset the game game which can be accomplished by pressing enter on the keyboard. This portion of the overall block diagram shows the schematic of the VGA show clock model. As you could see, this register takes two inputs, clock master and a reset, and the result is one output called clock VGA. At the rising edge of the clock master, the clock VGA will be set to 0 if reset sends a high signal, else clock VGA is set to not clock VGA. This portion of the overall block diagram shows the snake VGA model. Schematic. As you could see, this register takes two inputs, clock VGA and reset, which is initially set to low, and the result are 5 outputs: a 10-bit x-axis, 10-bit y-axis, clock, display area, and h-sync. The ultimate goal of this model is to basically generate the display area for our snake game. This portion of the overall block diagram shows the snake grid model schematic. As you could see, this register has one input named VGA clock. The result are 4 outputs: a 6-bit X point, a 6-bit Y point, 10-bit random X, and 9-bit random Y. This ultimate goal of this model is to generate the apple on the random parts of the display area. And at last, this is the overall block diagram shown all in one picture.
And as we were working on this project, my partner and I realized that there are some things that we could improve on. As you can see in the image on the right, this is a portion of the keyboard module for the system relevant code part of the project. This code specifically chooses which keys of the PS2 keyboard will correspond to which direction the snake will travel. So for example, if the snake wants to go up, the corresponding key we chose is W. If it wants to go down, we chose the key to be S, and for left we chose A, and for right we chose D. Each key on the keyboard has a unique 11-bit make code when the key is released, and an 11-bit break code when the key is released as well. The output is a 5-bit one-hot output in which the direction of the snake depends on the position of the one in the bits. And as you can see in the code here, each direction is denoted by a hex code, an 8-bit hex code. So for this hex code right here, called 1D, this is the code for the W key, which tells the computer for the snake to go up. For 1C, the key for that is A, for 1D it's S, and for 5A it's D. And as you can see, the 1 is in different positions for each key, and that's why it's called a 5-bit one-hot output. In our code, we made it so that when a certain key is pressed, the snake will move 5 units in that direction. However, we could have also made it so that just by pressing the key once, the snake will continue moving in that direction until another key is pressed. This would then take away the need for a break code. It will make it easier to keep track of the snake.
Up next, we have the video demonstrating our results. Alright, this is the way our setup is designed. We already load up the code. We got the DO2 board, got the keyboard, which is going to control the DO2 board unless we want to use these buttons. We can also use these buttons. And we have the HDMI connected from the VGA to HDMI connected to this screen. And this is the result. This is what we came up with.
As you can see, when we press this button right here, which is supposed to start the game, this screen will, the display area will show up. However, once you let go of it, it'll just go back to the reset screen, and that's because due to the border collision algorithm that we created. So once the snake touches any of these edges around the corner, it'll be game over. But the problem is, at the start of the game, the snake generates at the top left, as you can see here, and the apple alongside with it as well. That means that every time you start the game, it's game over every time. So as a result, this is the problem that we get, and that's the major difficulty that we're having right now.
So every time we reset, it generates in the corner, and that's the difficulty we cannot come across with. And that was it. As a result, again, when we choose to do this project, we thought it would be a great way to improve upon the skills we learned in CP200 lab. However, as we proceed with the project, we had many different ideas as to how to take the problem and come up with the solution. But in our level, we did not have enough knowledge to translate those ideas into our expected outcome. But even after the semester is over, our goal is to continue working on the project until we are able to overcome the difficulties we have initially faced.
Conclusion. Although we cannot get the program to work the way we wanted, we learned plenty of things in the process that will help us not just as UNLV students, but as future engineers moving forward. This project was a great way of demonstrating what we learned in CP200 Lab throughout the entire spring semester. More specifically, we learned how to create modules in System Verilog that could generate a VGA display, reduce a clock, and implement a program that would require an external input, which in our case was the PS2 keyboard. And that's it. Thank you for watching my presentation.
Thank you.